Hello and welcome to all students. Today in this lecture we are going to study about upper sum and lower sum of a function. In the previous lecture we defined what is meant by subdivision of a given closed interval or given interval. Now today we are going to define what is meant by upper sum and lower sum of a function. So let us write the definition. Let capital F be a bounded function defined on the closed bounded interval AB. Let capital F be a bounded function defined on the closed and bounded interval a comma b, and let sigma be a subdivision of closed interval a comma b. Then the upper sum of function f for function f corresponding to sigma is denoted by the notation u f comma sigma and defined as so we write the definition of upper sum and defined as so upper sum of function f corresponding to the subdivision sigma is equal to summation k is equal to 1 to n capital M F I K means this is nothing but the least upper bound corresponding to the component interval ik and into mod of ik. So this mod of ik is nothing but the length of the component interval ik. Okay, so this is the definition of of a function f corresponding to subdivision sigma. So if I expand this summation, then what we will see is, so if I put k is equal to 1 2 3 up to n, then we have n terms. So for first, if I put k is equal to 1, then what we have is m f I k into length of first. So here must be I1. So for k equal to 1, here must be I1 into mod of I1 plus second term is m f I2, f means small f, function f I2 into length of second component interval plus dot 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 plus, I will write now, nth component interval m f I n into length of nth component interval. So this is the expansion of this summation. So this is the definition of upper sum of a function corresponding to subdivision sigma. Now we write the definition of lower sum for function f. Okay, so next we write now lower sum of a function f corresponding to subdivision sigma is denoted by, let us write, lower sum for function f corresponding to subdivision sigma is denoted by the notation L f comma sigma, and it is defined as so I will write the definition for lower sum, and it is defined like this: L f sigma is equal to, it is also a summation over k is equal to 1 to n, summation of m f I k into the length of kth component interval. Okay, so mfik, this is small m fik, it is nothing but greatest lower bound of a function f in the interval ik into the length of the kth interval. Okay, so if I expand the terms of this summation, then we get, put k is equal to 1 up to n. So if I put k is equal to 1, then our first term will be m f I1 into length of I1 plus second term is m f I2 into length of second component interval plus dot 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 plus m f in into length of nth component interval. So this is the definition of lower sum of a function f corresponding to subdivision sigma. Now we write some note here. So note that the lower sum of a function f corresponding to subdivision sigma is always less than or equal to upper sum of a function f corresponding to subdivision sigma. So this is the important note corresponding to lower sum and upper sum. Now next we try to represent the lower sum and upper sum graphically so that picture will be clear. Okay, so let us write now the graphical representation of. So let us write here graphical representation of upper sum of a function f corresponding to subdivision sigma and lower sum of a function f corresponding to subdivision sigma. So first of all we try to represent a upper sum of a function f corresponding to subdivision sigma. Okay, so for that we draw a graph now. Okay, so in this graph, let us try to draw the graph for this thing. Okay, so see what we will do now. So we start from this point. Okay, from this point. Okay, this is our y-axis. 1 minute. Okay, y-axis, then we have x-axis. Okay, this is our x-axis, this is our y-axis. Okay, and now suppose sigma is a subdivision and this subdivision having a points. Okay, suppose sigma is a subdivision and this subdivision has points x0, x1, x2 up to xn n points. Okay, so that we get n component intervals on the x-axis. Okay, so let us start from okay, so suppose this is the origin. Okay, and suppose this is our closed interval a, closed interval a comma b. Okay, on the x-axis. Suppose my x0 is here, x0. Suppose my x1 is suppose somewhere here, x1. Okay, then suppose x2 is somewhere here, x2, x3 is somewhere here, suppose x3, x3 dot dot dot, and suppose this last point b is suppose xn. Okay, and f be the function which is defined on this closed interval ab. Okay, and if f is a function, then what to do is here now. Suppose there f is a function on this interval, and therefore it has some graph, some continuous function. So continuous graph, so as what is given to you, as f is a bounded function defined on closed and bounded interval. Okay, and therefore if is a continuous function, so draw the graph of that continuous function in this closed and bounded interval. Suppose this is the graph of the function on the interval closed interval ab. So suppose this is the graph of function f. Okay, so now what we have to do is simple thing. Okay, so our interval I1, so first component interval is from x0 to x1, and in this component interval we have to find the list. In this component interval we have to find the list upper bound of a function f. This is our function f. So we try to draw the trapezoidal corresponding to this component interval. So first trapezoidal is this. Okay, okay, so this is the value of, so this point will give us the value of least upper bound corresponding to first component interval. Okay, so it is m this value gives mfi1. Okay, and into mfi1. So as we seen in the definition, the first term of upper sum u f sigma is nothing but the area of the rectangle, and that rectangle is, we complete that rectangle here. We complete that rectangle here. Okay, so this is, so what is the length of this rectangle? The length of this rectangle is mod of I k. Okay, so product of these two things is nothing but the area of this rectangle. Okay, so let us shade this rectangle. Can you shade this? Yes, we make a shade. No, 1 minute, don't make a shade like this. We will shade this like this now. Okay, the first term of upper sum is nothing but area of this rectangle, and this rectangle is called as circumscribed rectangle. Okay. Now let us go to the next component, interval. So next component interval is from x1 to x2, and we draw a trapezoidal again. Okay, trapezoidal, and this point, the point on the graph, this point will give the value of mfi2, means least upper bound of a function f corresponding to second component interval. Okay, again we complete the rectangle circumscribed by this trapezoidal. Okay, so we complete this rectangle now. See here, okay, this is, and we shade the second rectangle and the area of, okay, so see here, and how to write the area of this rectangle, how to write area of this rectangle. So this value, 1 minute, I'm okay, just for understanding purpose. Okay, so this value is given by this point, this value is given by this point, and the area or the length of this rectangle is nothing but the mod of I2, and length of this first rectangle is, the length of this first rectangle is mod of I1. Okay, mod of I1. So now the second term in the definition of uf sigma is nothing but mfi2 into I2. So into mod of I2. Mod of I2 is nothing but the width of this rectangle, and mfi2 is nothing but the height of this rectangle. So we get the area of this rectangle. Okay, now we go to the third, now we go to the third component interval, and we complete this trapezoidal like this, and this point, so point at here will give us the value of, I'm writing here the value of m f I 3, mfi3. Okay, and mfi3 is nothing but the least upper bound of a function f in the interval I3. I3 is the interval from x2 to x3. Okay, now we again complete a rectangle circumscribed by okay, so we complete the rectangle circumscribed by this trapezoidal, and this rectangle is like this, so we go up to here, up to here, and not here, from I think we go up to here. Okay, and we complete this rectangle. Okay, and okay, and what is the breadth or width of this rectangle is nothing but mod of I3, or this denote the length of this rectangle. Okay, and the product of mod of I3 and MF I3 is nothing but the area of this rectangle. Okay, and the area of this rectangle we shade by using the color blue color. Okay, so see here, this is the area of this rectangle. Okay, so in this way, and the product mfi3 into mod of i3 is nothing but this area. Okay, and in this way we complete all n component rectangles, and we complete component rectangles. Okay, and the sum of all these areas is nothing but the sum of all these areas is nothing but the area under the curve approximately equal to the area under the curve. Okay, okay, so the sum of the areas of all these rectangles will give the approximate area under the curve of a function f, or we may call it is the approximate integration of the function f. Okay, so this is nothing but, so we go to the next now here. So we write here u f sigma is equal to m f I1 into mod of I1 plus m f I2 into mod of I2 plus dot 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 plus, so we have to find out all these areas up to in, means m f in into mod of in. Okay, and this is nothing but gives the approximate area under the curve. Okay, this is nothing but area, approximate area under the curve of function f defined on closed interval ab, or we can write it is approximately equal to, see here, what I can write here is it is approximately equal to integration over a to b of a function f of x dx. Okay, so this is the upper sum of a function f corresponding to the subdivision sigma, which gives the approximate integration of function f, over the over the interval a to b. Okay, so in this way, so this is the upper sum of function f corresponding to subdivision sigma. So upper sum is nothing but the approximate area under the curve, finding area under the curve. Okay, but this is the extra area which we will see here, which is not under the curve. Therefore this is not the part of the integration. Therefore we are saying approximate integration of a function f. Okay, so therefore we can write note here now. Okay, let us write one note. Notice that the area is extra, no? That's why our note is integration over closed interval AB of a function f is always less than or equal to UF sigma. Sigma is the subdivision of closed interval AB. Okay, this is the important note that we have to note here. Okay, now secondly we go to the lower sum of a function f corresponding to the subdivision sigma, and sigma is the subdivision of closed interval AB whose points are x0, x1, x3, dot 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 up to n points. Therefore we get n subintervals, and we again try to draw the LF sigma, means lower sum of a function f corresponding to subdivision sigma. Okay, go to the, now again draw x-axis, y-axis. This is our x-axis, y-axis. Then again go to the x-axis. Okay, go to the x-axis. Now this is our x-axis, this is y-axis. Both are perpendicular, origin, and suppose here it is A point, here it is B point, and we write the points in subdivision sigma. x0 is A and xn is B. Suppose x1 is here, x1, x2 is here somewhere, it may be anywhere, x2, and x3 is suppose here. Okay, dot dot dot, there are many points in between x3 and xn. Okay, we are only putting 3-4 points. Okay, and suppose the graph of a function f is, so we draw the graph as we have previously drawn. The graph may not be exact here. Okay, so graph must be same, so we try to draw same graph, but it may not be same. Okay, so suppose that graph is like this again. Okay, and we try to find the lower sum of a function f corresponding to sigma. So now consider the first component interval I1 is from x0 to x1, first component interval, and we construct a trapezoidal corresponding to the first component interval. Okay, so trapezoidal is from this point to this point, first trapezoidal, then this point, and this point on the graph will give us a value of m f sigma, mf sigma nahi, mf I1, sorry, mf I1. Okay, this point will give the value of mfi1, and if we complete the rectangle corresponding to this by taking this point, so we form a, from this trapezoidal we form a inscribed rectangle. So inscribed rectangle we form like this. So take a lower end of from these two ends and complete the rectangle, and this gives a inscribed rectangle whose height is mfi1 and whose length or width is whose length of this rectangle is mod of I1. And if I take the product of length and height of this rectangle, we get the area of this rectangle, and this is nothing but this area is nothing but the first term of in the definition of lower sum of a function f. So this area is nothing but the first term. Okay, so product of these two things mfi1 and mod of I1 is nothing but area of this inscribed rectangle. Okay, now again go to the second component interval and okay, go to the second component interval and find the mfi2. So where is the lower end? I think this is the lower end, or both are same. Okay, so I think this is lower end or this is lower end. Let us take this is the lower end, means let this is the value of, I don't know, this is the lower end, and suppose the value of this lower end is m f I2. Okay, and mfi2, and the width or the length of the second component interval is mod of I2, and product of these two things I2 mod of I2 and mfi2 is nothing but the area of inscribed rectangle. Okay, and that inscribed rectangle is, we draw this inscribed rectangle like this. See here, suppose this is the inscribed rectangle and this is the area, okay, which we left. Okay, okay, okay. This is second. Now similarly we do for third component interval. Okay, again find the value of this m f I3, and this value is given by this point. Okay, again find length of this third component interval, and the product of these two things is nothing but the area inscribed by area of inscribed rectangle. Okay, area of inscribed rectangle. That inscribed rectangle is here, and area is here is the area. Okay, okay, so in this way we do for all all n component intervals, and we made the sum of all these inscribed rectangles. Okay, and the sum is nothing but the uf sigma. So we add all these rectangles, areas of all these inscribed rectangles, and this sum will give the LF sigma. Okay, so this is our lower sum of a function f corresponding to the subdivision sigma, and this sum will give us the area under the curve, but not whole area. So it leaves this area, it leaves this area, it will leave more areas. Therefore it is not exact sum under the curve, therefore it is approximate sum under the curve. Okay, so we note here we write the note. We note that the LF sigma here, LF sigma, it gives the area, approximate area under the curve, approximate area under the curve, of function f on closed interval AB. Okay, therefore it is approximately equal to integration over closed interval AB of function f dx. And again we note one more thing, that this is our first note, and our second note is, as this LF sigma leaves some area under the curve, therefore so LF sigma is always less than or equal to integration over a to b of the function f dx. Okay, so this is very important note. So LF sigma is always less than or equal to integration over a to b f of x dx. Okay, so and we write very important note at the end. Okay, and that important note is, if UF sigma is equal to LF sigma, means lower sum of a function f and upper sum of a function f, if they are same, then we say that f is Riemann integrable. F is Riemann integrable. Then we say that f is Riemann integrable function on closed interval a comma b. Okay, so this is important, and in this case when UF sigma is equal to LF sigma, then UF sigma is equal to LF sigma, and the value of both the sums is nothing but integration over a to b f of x dx. Okay, so this is the definition of Riemann integrable function. If lower sum is equal to upper sum, then that function is called as a Riemann integrable. Okay, and one more we note here, the UF sigma is the sum of the area of the circumscribed rectangles, and LF sigma means lower sum is the sum of the areas of inscribed rectangles corresponding to the partition sigma. Okay, sigma is called as partition, no problem, or subdivision. Okay, so this is the end of our lecture. Okay, this is the end of this lecture. Thank you very much.